So today I want to make a brief presentation about Brownian motion and random walk. So let's see an overview of Brownian motion. So Brownian motion is a simple continuous stochastic process. It has many applications in either like the physics, economy, or like biology, and also like the mathematic finance for creating some math modeling and to describe some random behaviors. So this pictures is about just describe some like the physical behavior of maybe a small particle. It's like to do the Brownian motion. So the history of Brownian motion. Brownian motion gets its name from the botanist Robert Brown, who is a uh, who is observed this phenomenon during his experiment. Uh, so there is a picture of the Robert Brown, and um, yeah, he just discovered like under the microscope, he discovered how does like the pollens do the Brownian motion due to the reaction with the water molecule. So back to mathematics. In mathematics, Brownian motion described by the Wiener process. This is very important definition. And Wiener process is a continuous time stochastic process, which have the following four properties. So the first one is the Wiener when t is equal to 0 and a Wiener process is equal to 0. So we denote as W0 is equal to 0. And the second property is with p equal to 1, the function t, uh, the, uh, the function t can be continuous in all t, like the Wiener process. And the time t is continuous all the time. The third properties is a process of Wt. Whenever t is greater than 0, it has a stationary independent increments. And there is no definitions for like t is less than 0. That is meaningless. So I just, t is equal to greater than 0. So the last properties is about the increments. So every increments, like the W t plus s minus ws, which is has a time period t, has a normal distribution. Uh, we denote as the normal distribution 0 to t. And also for the third properties, it means like every process is independent, so they do not like dependent or depends on other. Like WT1 and WT2, they are totally different. Okay, so what is the random walk? How do we connect the random walk with Brownian motion? As we know, a random walk is a discrete time stochastic process. However, the Brownian motion is a continuous time random, the stochastic process. So the random walk basically it describes a path of like many random steps under a mathematical space. It can be ZD, which D is denoted as the dimension, and it also can be RD or something else. So for this, for the later presentation, I will just use ZD, Z. Okay, intuitively, we consider the Brownian motion as a limiting cases of some random walk as its time increments go to 0 because I just say like the Brownian motion is a continuous process. So when we connect the continuous process with a discrete process, we need to like use some. This is like the knowledge from the calculus. We let the delta t is tend to be 0. So here are two pictures of the random walk and the Brownian motion. As you can see, like the same period, during the same period, and Brownian motion and random walks is, if you just have a look, it will, these two pictures are very close, right? For the tendons, but the Brownian motion exactly show more details. That is a topic we may focus on later, because it has like many small partial parts. Also, there are many practical examples with Brownian motion as random walk. And in this presentation, I want to talk about the dimension 1, 2, and 3. And basically, I will focus on dimension 1 and dimension 2, since dimension 3 is much more complicated. So for the one-dimensional random walk, consider a random walk on a number line, which is just a straight line. So we can know for x, and we denote xp1 is equal to positive 1, and xp2 is equal to negative 1. So the p1 and p2 you can just think of as just go forward and just go back. So their possibility is equal, which are 1/2. So we have the expectation value for x, which is equal to 0. It's just positive 1 times 1/2 and plus negative 1 times 1/2. And also we calculate the variance x. We use this formula, and the variance x is equal to 1. So our goal is to describe a discrete random walk to continuous Brownian motion. So we can firstly set the discrete formula as this Sy. So by computer graphing, we can get a picture of the discrete random walk, which is exactly some point and without connection. So for here, I need to make some explanation about I. So I is just how many times you how many steps you separate. And as you see, this is 0, 1, 2, blah, blah, 2, 8. So I just separate for 8 steps. So we can simply connect all the discrete point with a line to get an estimation of the one-dimensional Brownian motion. But this is very rough. It's not a very detailed. So for getting a more detailed estimation of one-dimensional Brownian motion by the random walk, the new formula we define as this y bar. So basically, the t divided by n means we can divide t into n steps. So as you can see, the more parts we divide for t, and the more precise data we can get, and the more detailed graph will show for us. So we can get a more precise estimation of Brownian motion. So here is, if you just set n is equal to 5, it gives you a very rough. You see there is a straight line everywhere. So you can just get a very rough graph. You cannot get many informations. But however, in for if we set n is equal to 100, you can get a very detailed information. So like there, for this straight line, you can just see it passed further, like the original point for one time, for example. And for this pictures, you can maybe you can see it passed for many times, so we can get more detailed information. Okay, there are some practical applications. Like you may find the path of one-dimensional random walk go through the original position for many times, as we just discussed. This is because one dimension and two-dimensional random walk is recurrent. So this is very important properties for under the Z1 and Z2. Like we discussed before, is about the ZD when D is equal to 1 and 2. A famous example is a drink man will eventually find his way home. Okay, what is this? Let's see more detail. So as n goes to infinity, the oscillation, as I just discussed about the oscillation, and you will see more details, and like the time in a specific time with when n is increasing, you will see like more times it past the original point. So as n is equal to infinity, we can assume that t will just touch the original for infinitely times. Yeah. Therefore, for one-dimensional and two-dimensional random walk as Brownian motion, we can assume that the p, which is a possibility of the random sequence, when it's touched to the original point, is equal to 1, as you see here. So here is a picture for discretized Brownian motion path. And we just to make n very large and combine various passes of the one dimension. And here is a two dimension. Which different is this? Is a graph of xt, and this is a graph of xy. But they almost, you can see the path for the original for many times. And we do not just set it to infinity, but we just use a larger n to make some estimations. Okay, for the 3D random walk, as we already talked about the drink people during the 1D and 2D the random walk, we know that there are infinite times they can just go back to the original point. However, for our 3D model, it's much more complicated, and because you have x, y, z, so for the 3 dimension, the probability of coming back to original is actually less than 1. You cannot expect a people or like a bird, because people cannot fly. So let's think about a bird. You cannot expect a bird to just go back to original point for infinite time. So here is a proof, but it's really complicated. So I just said from the this professors or the doctors proof, this is very complicated. They use a triple integral and many algebras. Okay, so in today's presentation, I briefly talk about the connection between Brownian motion and random walk. Also introduce a realistic problems of drunk people to induce some properties of random walk and their different dimensions. I hope my presentation can help you have a clear understand of the Brownian motion and their connection between the Brownian motion and random walk. Okay, thank you for reading and listening my presentations.